be very interesting, see what people write. So thanks so much for having me here. I'm really honored to be here. It's great to finally be at a conference after COVID era. So we lasted 2 years waiting for this thing, basically. So very happy to be here. The organizers asked me to talk about two very different topics, the Lunar Dynamo and the Solar Nebula magnetic field. But what unifies them is that these are venues where we don't have magnetic fields today. So we're forced to understand them through paleomagnetic measurements of planetary samples. At least that's the current way that we can understand solar nebula magnetic fields until we get astronomical observations, which are probably coming soon. And the other thing that unifies them is because we have this paleomagnetic record, these bodies, these venues are sort of unfamiliar theoretically. We understand a lot less about them, how the fields are generated and what they mean. So there are a lot of really sort of interesting theoretical problems in here as well. So I made this funny slide here because I just figured the simplest way to do this is just give two talks that are somewhat interlinked, but not try to force the connections too much. And hopefully we'll get through both of them. I'm going to start with the Lunar Dynamo and then move on to the Solar Nebula magnetic field. Okay, but before I do that, since I know this is a mostly non-paleomagnetism conference, and for me, that's like a really great opportunity because I don't get a chance to talk to this community nearly as much. And so every time I go to a conference like this, I learn a ton. So thank you for inviting me for that. But I thought also it's important to just remind you how we, in a very basic sense, make these measurements, because understanding that, kind of helps you to understand, where we are with understanding the magnetic field problems in these bodies. So here I'm just going to talk about how natural remanent magnetization is acquired by a material that's cooling in the presence of magnetic field, something we call thermoremanent magnetization. Here I'm just depicting a solid sphere, maybe a chondrule, we'll see later, that's cooling in the presence of magnetic field. And if it's got ferromagnetic minerals, which in the case of the materials I'm going to be talking about are iron nickel minerals, you can think of them as little compass needles. They're not physically rotating, the electrons within them are rotating, and they experience a torque in the presence of a background magnetic field. But when they're hot, those electrons are waving around. If there's a paleomagnetic field of strength B0, then that exerts a torque on some of those electrons and aligns some fraction of them proportional to the field, that just gives us a magnetization M paleo. And it's because any sample I'm going to show you today, the background magnetic field we're talking about is uniform for sure on the scale of the sample. We expect the magnetization to be uniform throughout the sample. And it turns out that's a very powerful way of detecting the presence of a past magnetic field, looking for that unidirectionality in a bulk sense. Of course, the other extreme is there's no field, there'll be no magnetization in that case in a net sense. And so what we see is M is oriented toward B. So we actually can get direction of the field. Of course, I'm not going to be talking about direction today. I was just talking about Uli, though. Finally, in planetary paleomagnetism, we will have the opportunity to measure paleofield direction as a function of time with the Mars 2020 samples. It's another thing that I'm working on. We now have 12 samples that are oriented bedrock to better than 2 degrees, and we're expecting a full 30 sample suite spanning 2 billion years of Martian history of oriented measurements of the Martian magnetic field. It's going to be quite spectacular. But for now, we're only able to do intensity. And what we can infer from this is, of course, the intensity of the background field. And at least in the low field limit, we see that the magnetization is proportional to B, that paleofield, for some proportionality constant chi, which I'll come back to in a little bit. We can't measure chi very easily. So first order, it's proportional to the amount of ferromagnetic material, but there are other things in it that contribute to it. So what we do in all of the experiments I'm going to be showing you is we measure the natural magnetization M paleo, and then we artificially remagnetize the sample in the laboratory, hopefully in the very same way it was magnetized in nature, by heating it and cooling it in a magnetic field, because that'll have the same chi. And then we can get a M lab. And then if we take this proportionality of, we have 3 measured things here, M paleo, M lab, and B lab, we can get the ancient magnetic field B paleo, okay? All right, so that's the basis of all the work I'm going to show you today. Okay, so the biggest problem with planetary magnetism, paleomagnetism, is showing that you have a record that actually is persisted over geologic history and is consistent with an ancient magnetic field. And it turns out one of the most powerful ways of establishing whether something cooled in the presence of a magnetic field is actually seeing whether it's uniformly magnetized throughout its interior. Now, there are a lot of other criteria that we use to establish this, which I'm not going to kind of belabor here because I want to get to the records. But even this simplest concept that the magnetization should be uniform because the field is uniform allows us to basically very quickly often see whether a sample cooled in the presence of a substantial magnetic field. Okay, so we're looking for unidirectional magnetization throughout a sample on the, say, centimeter to millimeter scale. Okay, so let's get into the Lunar Dynamo. So the thing that's really interesting about the moon is it seems from both crustal magnetization data as well as Apollo sample paleointensity data that the moon's field was strong and long-lived. And that presents some conundrums for how you would power the Lunar Dynamo. And so the central question I think a lot of us are trying to answer right now is what was the power source for the Lunar Dynamo? And can we infer that by understanding the intensity history as a function of time? So this part of the talk is going to kind of be divided into two pieces. One, our sort of current understanding as of, say, 2017. And then a bunch of things in the last 5 years, some of which you're probably familiar with, some of which you may not have paid as close attention to. And then my thoughts about what they mean for our current understanding and the future work. Okay, so I think the first point I want to make with the current understanding is that I think it's hard to avoid that there were strong, and I mean greater than 10 microtesla, which challenges our current understanding of how this can be done, and steady, I mean long-lived, greater than a day, fields on the moon long ago, say between 3.6 and 4.4 billion years ago. I think each of those 3 points it's very hard to argue against them given the current data. But let's see if we can get into that a little bit more. So first, the lunar crustal magnetic anomalies. So what's important about this data set, we've had spacecraft going around the moon measuring the magnetic field of the crust. Of course, the moon doesn't have a dynamo today, so we're just saying pure crustal field. We know this magnetization originated on the moon. There's no contamination from the Apollo module or someone sticking a magnet on it or all the other problems. It's sitting in the Earth's magnetic field like we have Apollo samples. These are fields of the moon. And when people first looked at this, they saw that these fields seemed kind of weak, basically typically less than 10 nanotesla in most locations. However, most of the moon actually has anomalies that are above the detection limit and above about 1 nanotesla. So if you look at the scale, you can see that even 1 nanotesla anomalies are fairly ubiquitous. We think that that's robust. We're fairly sure that's robust because we can see it not just in magnetometry data, but in electron reflectometry data using a totally different measurement technique. The maps pretty much coincide. Okay, so we have 1 to 10 nanotesla magnetic field measurements all over the moon at 30-kilometer altitude. And Mark Wazorek and others have sort of looked at what the depth of those sources must be, at least outside the major impact basins, using a spectral analysis. And it's hard to conclude that they were shallow. They must have been, in most cases, on an average, at least greater than 10 kilometers in depth. And such a deep origin for the magnetization in a region that shouldn't have been disturbed to a large extent by large basin excavating impacts points to a very early magnetic field, maybe even during the first 100 million years of lunar history, during the original cooling of the crust. Of course, we don't have direct radiometric ages, so it's sort of an indirect argument. Okay, so first we have evidence for deep, ancient magnetic fields of the moon at 4.4 billion years ago. The second thing, and that's from the anomalies in the Highlands. So like things like here, for example, these kind of the ubiquitous 1 nanotesla crustal magnetization. But then we have things like this. This is the Crisium basin here with anomalies within them. And we know that these large basins probably heated the lunar crust above the solidus, probably the entire crust beneath them. So it's very difficult to imagine that those impact basins didn't completely remagnetize the crust beneath them. And so any anomalies in them, we strongly suspect must post-date the impact basins. And these are, reasonably well dated, and we can basically say that at least the Nectarian base anomalies, as they're called, indicate a field was also present at 3.9 billion years ago, probably ranging to 3.8 billion, for example. Okay, so that's the crustal anomaly record. Interestingly enough, not all the Nectarian basins are magnetized, only about half. And so that makes you wonder whether the field was steady during that time, or there are other ways of explaining that without requiring field variability. But just keep that in the back of your mind, that the record, although it's apparently ubiquitous on the moon, is still not obviously steady. Okay, so that's the first point I wanted to make, is that we have evidence from crustal fields that during the first 600 million years of lunar history. That's hard to avoid. Now, the other thing I want to say from the crustal magnetization is that it's hard to avoid that field being very strong, at least episodically. So this plot shows the conditions for producing a 10 nanotesla anomaly as measured by the spacecraft as a function of the ancient field that's magnetizing the material and that thermoremanent susceptibility factor, the proportionality between magnetization and field, okay? And then these curves here, these colors represent the layer thickness that's capable of producing this 10 nanotesla anomaly. So you see thick layers can have smaller field intensities and smaller susceptibilities than thinner layers in order to explain that anomaly, right? Okay, so now what I want to do here is put what we know about lunar materials from the Apollo record, which admittedly is not a complete record of all samples in the moon, but gives you a sense of how challenging this is to explain these anomalies. So let's start with what most of the crust is made of, the vast majority, more than 90-something% of the crust, which is this beautiful white feldspathic rock that you see when you look on the moon, surface up in the moon. What makes the moon white, what also makes it white is it's got very little iron in it. And these rocks have very, very low thermoremanent susceptibility. So some of the most weakly magnetic rocks that we know of. So this is kind of an upper limit. And then so I put that line there, and then these dashed lines you'll see coming up are what we think are the thicknesses of those layers. So where these two lines meet is basically would tell you the paleofield intensity that could explain the magnetization if it was being carried by an orthosite, for example. So you see they meet way off the surface, off the edge of this plot. So it would require insanely strong fields to explain the crustal anomalies if it's just normal, what makes up most of the crust, for example. Okay, we can say the mare. So the mare look like they're everywhere, but they're actually kind of a thin skin of less than a kilometer covering some basins and outside basins. And anyway, mare basalts, although they're much more magnetic than feldspathic rocks, are also still very, very weakly magnetic, even by the standards of Earth rocks. And so you see these two lines also meet way off to the right. We take the most magnetic materials brought back from the moon, which are the so-called mafic feldspathic, mafic impact melt breccias, which are thought to be mixtures of chondritic or impactor material and lunar crust. They're melts, basically produced by the large basin-forming impacts at the end of lunar history. These things just barely managed to do this, given what we think the thickness of the upper impact melted and gardened layer is, what we call the upper megaregolith, if you're allowing the field to get up to 100 microtesla. Okay, so this is not to say this requires strong fields, but it's very hard to do, is the point. And you shouldn't look at that weak lunar crustal anomaly map and say, well, that's so much less than the moon, and therefore the field must have been weak. In fact, it's the opposite. It's extremely difficult to explain that without calling on very strong fields. So maybe there are more exotic materials, but even so, it's going to be a challenge. So I'd say most anomalies indicate, 10 to 100 microtesla fields to be accommodated given our current understanding of lunar magnetization, rock magnetization. Okay, so that's just the crustal anomaly stuff, which I don't really work on that much. But now what I do work on quite a bit is the samples. And we have this beautiful sample suite of 380 kilograms. It's about to expand dramatically with the return to the moon. So what I'm telling you here, if you have another conference in 5 years, it's probably going to be super out of date with all the interesting samples coming back from actually, we already have a beautiful sample suite from China, from the near side, and they're going back to the South Polacan Basin, for example. So there's a lot more coming, but anyway, I think there's a lot we can infer already from what we have. So this is the Apollo era data. And these are not using a heating method in the laboratory. They're basically what's called using a strong field applied to the samples as an analog way of inferring chi. And it's not very accurate, probably maybe good to an order of magnitude in this case. But what you can see here, and I think this has stood the test of time, is that by Apollo era, I mean like 1980 and earlier, which is when most of the work was done. That there were the paleointensity measurements of the Apollo samples also indicate that there were strong fields in the moon, interestingly in the same range that you would infer from the crustal anomalies. If you take it, there also seems to be a lot of variability here in intensity, and also seems to be very long-lived. Maybe is going up to almost zero here, which is surprising given we don't have a field today. So I think there's a lot of uncertainties related to this. For example, mutually oriented samples weren't measured. The samples were heated in air when they were heated, and the ages were uncertain. We didn't understand a lot about the petrography of lunar samples and how what the thermal history of a complicated polymixed breccia with pieces of rocks from different ages and origins assembled into a melted thing. We've learned a lot more since then, but because of those things, I would say that these data very strongly suggest there was a strong fields in the moon, but exactly its origin and history and strength were uncertain. And actually, a very key important piece of missing evidence was what the lifetime of the fields were being recorded by these samples. So there was a large amount of discussion that maybe this magnetic field record here has nothing to do with a dynamo at all, but is the record of plasmas generated by meteoroid impacts that could conceivably generate magnetic fields because they're moving convecting fluids, in some general sense. So what was missing is what's important about that alternative idea that there were plasmas that just transiently generated this field is that they are transient, and even the most optimistic understanding of this would predict these fields would only last for a day after an impact. So unfortunately, there wasn't a lot of pairing of magnetic paleointensities with cooling rates to see whether the fields that magnetize these rocks were longer lived than that upper day, 1 day limit to really distinguish between the impact fields idea and the dynamo idea. Of course, there are lots of other exotic ideas that were proposed for lunar magnetic fields that I'm not going to talk about. Those are the two that sort of stood the test of time up until around, basically 2000 when a bunch of us got in the game. Okay, so we have strong, long-lived fields. We don't know their intensity or exactly how long they live, and most importantly, we're not sure whether they're, at the end of the Apollo era, whether they're a dynamo record or from impacts. Okay, or potentially, and this turned out to be another major problem, a lot of these samples we've now realized are magnetically contaminated. So we can see samples that were sawed at Johnson Space Center, and everything is sawed dry because they don't want to put water on it. And those saw-cut surfaces are often melted at the surface. And we've done careful studies where we can see when you take a sample from within a few millimeters of those saw cut, they've got a beautiful record of the Earth's magnetic field. So, identifying, and also we know that the Apollo sample module was remagnetizing some samples to not completely, but putting overprints on them because there were DC currents in the sample module. So you have to be careful about contamination issues. Fortunately, they're not. If you're aware of them, you can deal with them. But anyway, that's why there was something to do, is the point, despite the pioneering work here. Okay, so this is what I'm going to call sort of modern paleointensity measurements as of 2017. And then the last part of the talk, I'm going to talk about 2017 on. So these were samples that we could date, that we knew their cooling rates, or we measured them. They had simple thermal histories, and these are again using non-thermal paleointensity methods in most cases, though. So what you can see here, though, is that evidence for a strong field seems to be robust. And now we know that, I think with high confidence, that field was certainly steady. And it's really hard to explain this by some kind of plasma-generated impact field. So I think this more limited data set, and by the way, these red points are all upper limits. So we see evidence for a strong field here. So, and then, at least as of 2017, nothing after that. Okay, so let me say one other thing about this. Okay, no, I think I have a bullet there. All right, so let's first explore what this means. So these fields are, if we believe these paleointensities, these are sort of 1 sigma up uncertainties. So they're fairly high uncertainty because of the lack of heating. They seem to be too strong to explain by the simplest idea that the dynamo is powered by core crystallization, some kind of convective dynamo. If you really push the parameters from Uli's or other people's scaling laws, maybe you could get 10 microtesla. That's extreme. It's probably more like in the 1 to 0.1 microtesla range for the moon. So these points are essentially they seem impossible to explain by a typical core crystallization dynamo. On the other hand, the nice thing about the core crystallization dynamo is that it could potentially persist throughout all of lunar history. So although it's not inherently very powerful, it is potentially long-lived for the reasons that I'm sure you will understand. Okay, so but it's possible that it wasn't a continuous core crystallization powered dynamo here. Maybe it was episodic. And then maybe on an average sense, the power is compatible with what we understand. And that's an idea that's gaining increasingly strong attention, as you'll see. I'm just posing it right now. Okay, so but maybe you might argue this is a more straightforward, or you might argue it's a less straightforward solution to this, which is that there are other power sources around that are huge compared to what we understand for core crystallization. And maybe the most important one of these, people like Dave Stevenson and others have worked on, is the idea that the precessing mantle can stir up the core mechanically and generate strong magnetic fields. The main limitation is that because of the evolution of the lunar tilt and evolution of the lunar semi-major axis with time away, that power drops. And so it's probably only available in a significant way for the first few billion years of lunar history, with the obvious caveat that lunar orbital evolution is a challenging topic to understand, to actually understand in detail. The big challenge, the precession dynamo, as I think, imagine most of you know, is whether that power is actually put in the right place with the right kind of motions to actually have a self-exciting dynamo. But the power is there. Okay, so now let's before we move on to the second part, let me just talk about what's our limitations right now. Okay, so first of all, most of these, with one exception, is basically non-thermal methods, so our uncertainties are fairly large, particularly for these blue points. Factors of 5, 2 sigma, and let's say derived from a kind of empirical relationship. Secondly, most of these samples are they're not the ideal magnetic recording devices. Without going into detail, they tend to be multi-domain. So there's a number of problems with samples of multi-domain grains. So the metal grains are too large. They get overprints on them from subsequent sample exposure to even modestly strong magnetic fields that are hard to remove, that could confuse you as being an ancient record. The other obvious thing is that there's almost no points after 3.5. And then we've wondered for a long time whether these points are actually biased. And the reason we've suspected that is that when a bunch of us first got into this, our goal was to see, was there a lunar dynamo or not? That was the question, not really what's the intensity and variability with time. So I think we naturally gravitated toward samples that Apollo era data suggested had robust field records. I'm not saying we did this deliberately, but in retrospect, just to see whether we could even disprove that or build confidence in that. So if it's a hypothesis now that maybe these are biased, and maybe in the sense that we haven't looked at the way we chose the samples. The measurements themselves are robust, but the way we selected the samples may have been biased. Okay, so it's important to kind of build the data set here without just sort of randomly getting samples, as long as they have the right recording properties. Okay, so that brings me to part 2. Okay, so part 2 is, what do we know now since 2017? And so there's some interesting new discoveries and some puzzles, and they tell us about, I think, field variability and certainly evidence for recent magnetic fields. Okay, so the two big things that I think we're learning now, robustly the field persisted beyond 1.5 billion years ago, I think. Maybe a little bit less strongly, but likely to be either refuted or greatly strengthened in the next few years, is that the field intensity was likely variable by factors of 10 to 100 potentially. Okay, so there's a lot of different things going on, but I think I wanted to highlight 2 important technical advances that are allowing us to make progress in this. So first is the development of the use of reactive gas mixing. So basically, heating the lunar samples, not in air, which is way too oxidizing, but maintaining the oxygen fugacity of the environment so that the metal doesn't rust, the silicates don't get reduced. Then the other thing is, related to that, there's also single crystal analyses that are coming online from the group in Rochester. Then the other thing is a new archive of samples that allow us to actually probe late lunar history. The problem was that, the Mare basalts and the Highlands rocks are all very old. So the moon basically cooled off quickly and there wasn't a lot of geologic activity after about 3 billion. And also we landed on some very specific locations on the moon. And so we lacked, samples that formed, rock samples after that period. The only samples we had are basically impact melted agglomerations of regolith, which were largely unexplored as a paleomagnetic target until relatively recently. But the cool thing about them is you'll see is that they are young, and then they also have this very nice magnetic recording property, at least the matrix, the black glass. Okay, so just to tell you why I think this gas mixing is important, most heating experiments have been done in air, which is, of course, basically has an oxygen fugacity at 500 C of 21 orders of magnitude above what the rocks formed in. So it's extremely oxidizing. There were attempts to heat them in the purest argon you could find. That's even worse, as it turns out. 24 sorry, I meant to say this is when you're doing it in a vacuum. So if you did it in air, you'd add 8 orders of magnitude to this. So even the best vacuum, you're getting 21 orders of magnitude to oxidizing, partial pressure. If you do it with argon, it's even worse because you can't get pure enough argon. Other people tried to mix hydrogen and argon, and that's too oxidizing, as it turns out, too reducing, excuse me, because you basically have a reducing gas. So basically, all these things are way off what we know the rocks formed in. However, the paleomagnetic, and this is very different, of course, from Earth samples, where most of our techniques have been developed. So it's not surprising that these techniques were tried first. It's just not appropriate for lunar samples. But the petrology community has known about this for decades, and they've developed reactive gas mixing, where they mix two gases that continually react over a range of temperatures. And by determining the gas mixing ratio, they can set the oxygen fugacity to pretty much the full range that planetary samples are known to have formed in. And so we implemented one of these things in a non-magnetic oven with a paleointensity coil so that we could actually do heating and cooling in this. And we've used hydrogen and CO2. Now other groups have also started doing this. And we can mix these things over this full range and basically go all the way from 1% to like 1,000 times lunar conditions. And so that we can basically start doing these paleointensity experiments, at least mitigating the oxidation reduction reactions, if not all other things that can happen, which are non-oxidative and reductive. Okay, so we also can do this relatively quickly. So just to convince you, hopefully, that this works, if you take a Mare basalt analog, so a metal-bearing sample, that has a thermoremnant magnetization formed in the Earth's field, and you demagnetize it in air, its minerals should demagnetize at their characteristic Curie temperature, which for metal is 780 C. So this plot here is showing you the intensity as a function of temperature. This inset showing you the direction of the magnetization of the sample on a unit sphere, with symbols in the center corresponding to up and down directions, and symbols on the edge corresponding to horizontal directions and various azimuthal directions. So okay, so what you see here is that there's this magnetization, and then by 700 C, 600, 700 C, it's essentially dead. So, but what's happening here is that that's well below the Curie temperature. You're basically just rusting the metal. So you're not demagnetizing it, removing its record thermally, you're just destroying it. And if you put that in a controlled atmosphere, you see what we expect, that it persists up to 780 C. Okay, and we've Curie temperature, or of camosite, the iron, low nickel iron, which is a ubiquitous ferromagnetic here, BCC iron. Yeah, I appreciate questions like that. So just jump, that because sometimes I assume things that, that I think this community may not know, and probably sure I'm saying things that you guys know much better than me. So I appreciate feedback like that. Okay, so the other thing that's important about this is, as I said, these regolith breccias. So this is 15498 from Apollo 15. They have this beautiful black glass, which we found on the Earth. This glass tends to be great paleomagnetic recorders because it has fine metal grains. And this should have a thermal remnant magnetization when it was assembled as a rock, as a breccia. And we can look at that glass and see these tiny little metal grains are right in the size range that we love. Okay, so just to remind you, we're looking, if there's a field present, we have uniform magnetization. If we have no field present, it's going to be scattered and weak. And for 15498, that sample we have, we take mutually oriented subsamples. We see this fairly unidirectional magnetization consistent with the presence of an ancient magnetic field. And that's from that melt glass. And we can infer its intensity from those controlled atmosphere measurements. And we get 5 ± 2 microtesla at 1.5 billion years ago, so quite recently. Then we have, as we do this on a couple other glassy regolith breccias, they have totally different magnetic records. You just take a piece and it's pointing in different random directions compared to the next piece right next to it. So just looking at the directions of these pieces, you can see that this did not form in a strong magnetic field, right? And if you measure its paleointensity, you find that it's exceptionally low, say certainly less than a microtesla. Depending on which technique you use, you could say it's even less than 0.1. And these were dated at 0.9 and 0.4 billion. So even more recently. Okay, so there's those 3 points added to the plot there. I forgot to mention there's also this point from before 0, which we'll come back to, so you see now we have this 1 point right here seeming to extend the dynamo by 1.5 billion years. Of course, it's a single point. Interestingly enough, it's below the core crystallization upper bound, so maybe compatible with a dynamo powered in that way, easily compatible. So now we've got a bunch of other samples coming online. None of these are yet published. They're in various states, and there are actually 2 different groups represented here. But you see, we're starting to fill this in, and the picture is a little more complicated, but you still basically, the main thing you want to see here is that the fields are uniformly weak at this time. The error bars on the age are our main problem now with these samples. So there's a few hundred million years uncertainty in typically these measurements. But broadly speaking, we have now 3 samples that are all consistent basically with a late lunar field, and they have these nice magnetic recording properties that are not altering during measurement. Okay, so maybe we now see evidence, growingly strong evidence for a late dynamo, which seems to be difficult. Maybe you guys can tell me whether you agree, to do with precession. Maybe is the kind of evidence that you'd like to see to motivate something, a longer lived power source like core crystallization. Okay, and then if you look at all these together, there's some evidence for field intensity. If you look at these error bars and you stretch the points to their maxima, you can get there to be basically a monotonic history, but it requires stretching all of the error bars to their limits. The joint probability of doing that is quite low. So I would say, this is circumstantial and likely to be strengthened evidence if we get more data like it, that there is quite a bit of variability in the late lunar field history. And even these points are hard to explain by a core crystallization dynamo. So we really appreciate that if we want to understand this. Okay, so I think that's starting to become an interesting observation that we'll see more of soon. Okay, then there are these new measurements from the Rochester group. So these are basically 2 classes of measurements, early samples and then a young sample. A caveat is they were done in air without mutually oriented subsamples. Let's just consider them at face value and see what they tell us. So we have basically 5 upper limits here that are all saying that there's no magnetic field that's present. Interestingly, 2 of these are from the period when we have high magnetic fields in the moon. So that may be giving us evidence that there's even stronger variability in the early history of the moon. Perhaps even more intriguingly is this guy here. So this is a sample that's 2 million years old. It's an impact melt, and it's got what looks like a very nice paleomagnetic record. It's an impact melt, and it's formed in a field of like 20 microtesla. So either there was a field 2 million years ago and we have special observer status, or there's something funny going on here. What's also important about that sample is they did both thermal and they did non-thermal methods. So you can't argue that that's from alteration, even though they did it in air. They get the same result when they use non-thermal methods, which I guess is comforting for those of us who've used both techniques and combined the data, that in their case too, they're seeing the same thing, that they agree, okay? Okay, so first thing is we see this potentially enormous field variability, which is nice from a theoretical perspective in that it seems to relax the power requirements if it holds up. Again, only 2 points in air, but hopefully we'll see more evidence coming this way to robustly test this soon. There's plenty of samples to do it. And then there's this 20 microtesla field at 2 million. So the authors, and I think this is a reasonable hypothesis, suggested that this is the first evidence for impact generated magnetic field of any planetary sample, that this is, couldn't be from a dynamo. Now, the trouble with that is that there is a theoretical study, a numerical study, suggesting that charge separation in plasmas could potentially generate magnetic fields from the size of the crater that produced this sample. But that very same theoretical study also predicts that the fields, and this is something that's consistent with our understanding of this, are super short-lived, like less than a second, like 0.2 seconds. Yet the cooling timescale of this sample is, seconds to minutes, essentially, depending on how you calculate it. It's even been measured directly, actually, from petrologic experiments. So I think if this is an impact field and it's working in a way that we just fundamentally don't understand, it actually doesn't even make sense with the theory that's been produced to supposedly support its existence. But anyway, there aren't many options here. The other option, the only thing I can think of, is that somehow this is some kind of sample contamination, which I have mentioned is a problem. But fortunately, I don't think we're going to have to be perplexed by this, because there's plenty of material, and this measurement should be reproducible if it's robust. So anyway, I wanted to point out that it's extremely interesting, and hopefully we will have some consensus about what it means soon. All right, so just to bring this to a close, we may have multiple evidence for multiple dynamo mechanisms, maybe a precession before 3.5 billion, or perhaps an intermittent convection dynamo that's basically not energetic for most of its time period before 3.5. And maybe a core crystallization dynamo after, which could be easier accommodated with the weak paleointensities and the long-lived nature. Or there's probably lots of other ways of doing this. So, motivated by work by people in this audience, maybe the dynamo, we were talking about this yesterday, it was in a bistable state going between the weak field and the strong field branch. I don't know. And so there was a single mechanism in that case. You can tell me whether that's easily disprovable or not. Okay, so conclusions. There was an intense field. I think it's very hard to argue against that, even given the imperfections of the data, before 3.5 billion years ago. The possible explanations are that there was a core convection dynamo intermittently strong, or a non-core convection dynamo. We like precession. There have been other interesting suggestions of a silicate magma ocean dynamo that under high pressure could be conducting and has the advantage of the dynamo region being closer to the surface, so it's less attenuated by the dipole field fall off. I should mention, the thing that makes this harder, I should have said this in the beginning, is that if you calculate the local Rossby number for the moon, you find that it's in the multipolar regime. So if we accept that that is what it was, which of course I think is not at all required, as Uli and I were talking about, that makes the extrapolations to the core even more crazy, and the field even harder to explain in intensity, right? Okay, but anyway, so I'd like to know what you think about that during the discussion and answer session. And then it's always possible that these high paleointensities are wildly inaccurate. I don't think that's the simplest solution, given what I understand about the rock magnetic data, but more importantly, it can explain the crustal field. Okay, and there's a long-lived field, maybe it's precession. There's an idea that there might have been plasma magnetic fields very recently. We can test that idea with more sample measurements. Okay, so that leaves me with 20 minutes to do the Solar Nebula. I'm going to try to, I think it might let me leave it to the audience. We want to have like a 20-minute just discussion now about the moon and then just forget about the solar nebula. You know, I was making this and I didn't want to make these two trivial talks. I wanted to dig into this, and but I knew I was going to be a little short on time when I got to this section.
So it might be a good idea to handle any questions. Yeah, it might be a good idea to handle any questions right now about the moon. I know about this topic, it's a very different topic, although some of the measurements that you want to make are closely analogous, but in terms of physical process, the moon is a very different story. So are there any questions? I have a comment. Presumably you would like to get more data. I mean, Apollo is somewhat biased in terms of both time and location. Do you have a comment about future data that one would hope to get from the moon, which means samples, of course?
Yeah, so already we have an interesting sample suite from China. They went to a very young Mare. So, and those samples are 2 billion years old. I know I was just at a conference where they reported some results from that. Did you see their talk, Kathy? Because actually I wasn't at their talk. I know we were both at the same conference. So, okay, didn't mean to put you on the spot there. Okay, anyway, so I talked to I missed their talk, but I talked to them beforehand, and they were saying that they have evidence for magnetic fields in their samples at 2 billion, so that's nice. We also have probably going to be South Pole Aiken sample return from either the US or China. Ideally, we would get bedrock samples, and I think as a community, that's what we should advocate for, that if we can have the opportunity to take oriented samples and actually get directional sequences from the moon like we have from Mars, we will have from Mars, that would be the most important advance that we could have. So, you know, then we could start not just looking at intensity, but, you know, look for reversals, you know, secular variation, all kinds of fun things. So I think given that we're launching a mission every 2 years and there's, you know, and on private payloads in the US and Artemis, I think it's in 10 years, we will likely have oriented samples. And maybe that's optimistic, but I think it's not.
Kathy, I think, hold on. Just entangle myself. Here you go.
Thank you. So first of all, I love it that you say 2 billion years is very young. I've got 2 questions which may not really be very fair to be asking you since you're on the experimental side of this. But when you're talking about the crustal field, there's a huge ambiguity in there because of Runcorn's theorem.
Yeah.
And that presumably makes things worse.
Yes, good point.
And I was wondering if you had any comments on that. And then the second question, which is not quite related, is you put the precession dynamo as somehow stopping at 2 billion years, and I didn't really understand what the origin of that theory is.
Yeah, you see, I'm glad that we're doing this question now because there's a lot of things I couldn't explain. Mm-hmm. So those calculations for the minimum paleofield to explain the anomalies make very optimistic assumptions. That's why they're minima. So you mentioned Runcorn's theorem. You know, more broadly speaking, we're also assuming, in addition to that, this is a uniformly magnetized layer, which is extremely unlikely for something so thick, given any field variability that we might dynamo field variability that we might expect, and not to mention physical rotation of the crust by billions of years of basin forming impacts. Hundreds of millions of years at least. So as soon as we add all that stuff in, it gets harder, is the point.
Yeah, I mean, if you have a uniformly magnetized layer, you're going to have no net field.
Yeah, if the whole moon is like that. But I mean, if it's just a localized plate.
So you're looking at the contrasts in the magnetization.
Yeah, exactly. Yeah.
Let's imagine that you actually have a very deep magnetized layer and then so strongly magnetized, but then all you need to appeal to is imperfections in that magnetization that break the theorem. So you have a sort of strongly magnetized hidden layer, which you just then, I mean, I'm not saying it's the way, but if you hit it with impacts, you then create edges where you break the theorem. So I'm not sure it makes it harder. I was wondering whether it actually can help you in that respect.
Well, it limits the fields to edges, like you said, not
Right.
spatially uniform over large scales. So it doesn't make it that much harder. I agree with you. I think the bigger problem is the uniform magnetization assumption for a limited plate, which is why we can see it. Not talking about a whole sphere, which would be silent for the reasons you're saying. So,
Ben, in the beginning, you showed the map with this homogenized layer, but there's a lot of other stuff, peaks, whatever, much stronger magnetization, right? By the way, from which spacecraft is that?
what's the spacecraft that
Yeah.
produced this? So that's mostly Lunar Prospector.
Okay.
So this is the map you're talking about?
Yeah.
Okay, and can you say again what you're
So
referring
all these peaks you're showing here, you didn't talk about them much.
No, I
Is
didn't.
that correlation with, is there correlation with some impact craters or
Yeah.
some topographic features or
Right.
whatever?
So I wasn't talking about the most magnetic anomalies, which are completely hard to explain, right? I'm just talking about the average magnetic anomaly in the moon, just showing you that even that is a huge challenge. And then you get these things like Reiner gamma, which I think is right here. So, we have hundreds of nanotesla. And then this huge province here, which is the South Pole, around the South Pole Aiken Basin anomaly, so that's a fascinating magnetization because it was noted early on that that's antipodal to 4 out of the 5, so on the opposite side of the moon, from 4 of the 5 largest late lunar basins, right? And so people were skeptical of the dynamo. We didn't even know if the moon had a core for much of the Apollo era. Okay, so that's how skeptical they were. And so they were trying to think about how can you explain that so strong, and maybe we don't even have a core. And so they noted this geometric association, and that actually was one of the first motivations for the idea that this was a record of an impact magnetic field. In this case, the idea was basically a plasma produced on the antipode. It's basically conducting fluid, and it just, by the frozen flux theorem, concentrated the field lines at the antipode. And so this is a manifestation not of anomalously high chi, not anomalously high ferromagnetic material, but anomalously high B, okay? So we actually, I didn't mention this, we did that was never modeled in any detailed way. It was just sort of like, it was a picture, and I'm not trying to disparage it. It was just an idea, a creative idea. We, a couple of years ago, actually used the BATS RS MHD code out of Michigan with some of the people there to model that. It turns out you can't get the fields anywhere as strong as they proposed you could. So I think that idea is probably dead. I think even people who put it forth accept the idea. So that leaves still the problem of explaining these. And I think the more parsimonious explanation is that it's a high chi. There's tons of ferromagnetic material there. And in fact, if you have this is sort of downrange of the elliptically shaped so-called South Pole Aiken Basin, which is the largest impact basin in the whole solar system. And you can calculate the amount of meteoritic material that would be deposited. You can estimate that. And this could be explained by a substantial magnetic field, 100 microtesla, tens of microtesla, and then basically impact melt and debris, which is very non-magnetic lunar crust polluted by the huge impactor that basically produced this. So I suspect a lot of this stuff, which we said is all of this stuff here, I know all is a strong word, much of this stuff still requires strong fields, and remember, and very magnetic material. So we think that very magnetic stuff that most likely is exogenous material in many cases. It makes sense given what we know about the flux of materials to the moon.
Perhaps we should move on, but I'll make a brief comment about process. The precession idea makes sense for the early history of the moon because we know that the moon is moving away from the Earth, and the precession rate and the magnitude of the effect actually depends on the distance between the Earth and the moon. What we don't know is the history of that movement. We know, of course, what it's done recently. You can also look at the length of day, and there's ongoing work on that very interesting question, because we think that the Earth started out with a length of day that some people think is as short as 2.5 days. Others would say 5 days. Anyway, now it's, hours, 2.5 hours, 5 hours. Now, of course, it's 24 hours. But that variation is tied through angular momentum, approximate angular momentum conservation with the distance between the Earth and Moon. So precession is intimately connected with our understanding of the history of the Earth-Moon system. Core convection makes most sense if the core is not pure iron. And that's possible, but it's important to keep in mind that the Moon is volatile depleted. There's not much sulfur. Sulfur is the natural component to put into iron, along, of course, with nickel at low pressure. But sulfur is the way that you can get phase separation. It's what we think is important for Ganymede and, of course, for Mercury, for example, in Uli Christensen's work. We heard about that earlier. And you do need cooling, but you don't need a lot of cooling if you have formation of the inner core. Observationally, there is no doubt that the Moon has a core. It's about 350 kilometers in radius. That comes from geodetic data, lunar laser ranging data, which has been collected over a period extending all the way back to the time of Apollo. So there are some observational constraints. It's not purely theoretical. Anyway, enough said. Why don't you talk about the nebula?
Let me just ask, I think it's going to be difficult to do the other subject justice, so I'm happy to, I don't think I'll talk about that. I appreciate the offer to do so. So let me just use the last few minutes to just ask you a question. There's no, so do you agree, or maybe I shouldn't even try to bias this. It's impossible that, is it impossible that the Moon is basically such an extremely weak dynamo that we wouldn't see it today? So producing surface fields less than a nanotesla. Do you agree that that is something we should not consider seriously? That's part A. And part B, or is it conceivable that it could be basically off today, but with the likelihood that it could be restarting fairly regularly in a stochastic nature over the last billion years? So the reason I'm asking that is coming back to that young lunar glass measurement. Depending on what we find about that, if that is a robust measurement, then we know in principle core crystallization has the capacity to have a dynamo even today under certain parts of the parameter space for understanding that. So maybe, there was something 2 million years ago. There's no special observer status because it's just turning on and off. I'm just speculating here, but is that something that can be fairly readily discounted, or is it something to consider? So that there is a dynamo today that's insanely weak beyond everything we know it should be based on scaling laws. Maybe it's somehow screened in some way, or is it possible that it's in some kind of start-stop regime that would permit the data that we see? David, I guess you should call on her.
Still have something more on the Moon. Gonna run out of time to talk about.
Yeah, there's no way I can do that because I only had an hour. So I do. I have a whole second half of the talk.
Okay, so working on using up the rest of your time. I think the question you're asking is, could there be a hidden dynamo? Mm-hmm. And that, in my opinion, would come back to the thing that Andy and I came to, and you would have to have some idea of what the consequences of the impact craters had been on the non-uniformity of whatever is producing the crustal field. Because if you could have a hidden dynamo, I think, if you had the crustal magnetization basically shielding what's going on here, and you would have no signature of it in the crust.
The trouble.
So from the crustal magnetization perspective, I would say it's still an open question what you've got from the paleomagnetic perspective, because you actually have so few observations that you don't have anything that's statistically representative.
Right, I agree with that. One comment about that: the challenge for that there is a dynamo today idea is, and I didn't talk about this. So these I showed you magnetometry measurements, which are made at tens of kilometers altitude, right?
Sure.
So we have these electron reflectometry measurements, which use the electron mirroring effect to measure directly at the surface, right? And so they're exceptionally sensitive probes of the magnetic field. And what we can see is in decent fractions of the lunar surface, particularly the Procolarum creep terrain area, the near side of the moon, the field is for sure less than 0.2 nanotesla. Okay, so that's the constraint. Even though there's crustal fields up to hundreds of nanotesla, we know in a global sense, we can probe in the weakest, where we'd see through that noise that you're talking about, the field must be less than 0.2 nanotesla. So we're talking like, less than the interplanetary magnetic field. So I mean, that would be hard to explain in a normal dynamo. Understand my amateur idea of how dynamo works, but I'm just curious whether this audience has more creative suggestions to that. So anyway,
We're running out of time for the nebulous field, but
there's no way.
but of course your title was the moon, so that's okay. Looks like it's going to just be the moon.
Yeah, I don't think we can do that.
Concerning this question, I mean, if you look at these scaling laws from Uli and others, they predict there is a certain minimum field strength, which has to do with, you need a certain magnetic Reynolds number to drive the dynamo.
Right.
And then that gives you a certain
Yep.
minimum field strength. So the size you were mentioning, that is just not conceivable
Right.
with such a type of dynamo.
It's not self-exciting, essentially.
Yeah. And so, of course, there is the idea of a weak field dynamo, and we have seen different states. So if you refer to the weak field dynamo I have been showing yesterday, for example, this is about 10% of a typical dynamo.
Yeah.
So it's couldn't explain that. This is, multipolar field components versus dipole or whatever, right?
Mhm.
And of course, there's a geometric effect and so on. So maybe a bit more, but well, again, not an explanation. There's, of course, this may be not a real weak field dynamo in the sense that theoreticians talk about that. Yeah.
Yep.
So it could be much smaller if the saturation mechanism is wildly different from what we see in the simulations.
Mhm.
I would think this is likely, but maybe the theoreticians could say a bit about that.
Okay. So anyone who would like to hear at some point about the Solar Nebula, I'm happy to talk to you at some point during the conference. Thank you very much for the opportunity to speak.
Thank you, Ben. And David.